Hello Chem 1B, this is Chapter 18, Lecture Video 8, and we're going to start off by talking about standard state. So the standard state of a substance is really just a defined state, right? It's the state that when two research scientists compare their work, if they say they're under standard conditions, this is what that means. Now, for a substance that's in the gaseous state, it means that we're at 1 atm of pressure. And if we have a substance that's in a solution, i.e. like dissolved, aqueous, mixed together with another liquid, then we know it's at 1 molar concentration. Now for both solids and liquids, we assume they're pure. All right, so for instance, solids can be impure. If you think about like a metal alloy, we have two metals melted together and they're mixed together. That wouldn't be a pure solid. It would just be a mixture of two solids in the solid state. So in standard state, a solid would be the pure substance. Now, this also assumes that we're at 25 degrees Celsius. Now, some of this you should be reviewed from Chem 1A when we were covering thermodynamics in that class. And we're always at 25 degrees Celsius for thermodynamics when we're talking about standard state. However, with delta G, we can actually correct our standard state for temperature using delta G is equal to delta H minus T delta S. This can technically be delta G calculated under standard conditions, just not at 25 degrees Celsius. It's possible to do that. So that's pretty much standard state. Now, why is that important? Well, if we think about delta G naught, this little zero here up top, that means we're under standard conditions. We can calculate delta G naught for a reaction using Hess's law. We can correct this delta G for temperature using delta H minus T delta S. But at the end of the day, most reactions that we do don't generally have 1 molar of concentration solution, and we're not usually exactly at 1 atmosphere of pressure. So it's very useful to be able to calculate delta G without this little zero here under non-standard conditions. And so far we haven't done that yet. If we want to change either one of these two, concentration or pressure or even temperature. Temperature we can correct for a little bit already. But if we want to have these not be 1 atm or 1 molar, which most of our systems don't operate at these two conditions, then we got to do something else. And so we got to kind of edit our equation and have a new equation that will take into account both pressure and concentration into the equation. Now that new equation looks like this. Now we have two delta G values here in this equation, right? So we have this one here and we have this one here. The difference is this guy has its little zero buddy, which means this guy is under standard conditions. Whereas this one, no little zero next to the blue delta G. This is non-standard. And so we have this whole thing going on, right? So this new equation involves the standard delta G plus R. This is our ideal gas constant. But it's in 8.314 joules over moles times Kelvin. This is temp. Has to be in Kelvin. And this guy here is Q, which we learned in chapter 14 is our reaction quotient. This guy was the thing we compare Q to K and all that. Now it's in an actual equation. So these are all of our parts, and this is what we'd need to do to calculate delta G naught. again, so just like I just said a second ago, right? Q is the reaction quotient. So we can actually see all that. All right, so this equation we need to be able to use. And in order to use it, we need to be able to calculate Q. And we need to have this value here. These two usually we're given. So let's do a problem. So let's say, hey, we want to calculate delta G specifically. Notice no little circle here. It's not there. Now we're calculating delta G under non-standard conditions. So you need to be kind of looking out for that delta G naught value. If you don't have this little circle there, then that means something important. We're told we're at 298 Kelvin, so there's our temperature, right? So there's T. For a reaction of nitrogen with hydrogen to form 2 moles of gaseous ammonia. If the reaction mixture consists of 0.5 atms of N2, 0.75 atmospheres of H2, and 2 atmospheres of NH3, and your delta G naught of formation of nitrogen or ammonia, is negative 16.66, we want to calculate delta G. Now, how do we do this? The first thing I need to do is I need to get delta G naught of my reaction, which we know is equal to the sum of the products, delta G naughts of formation, right? Products minus the sum of the delta G naughts of formation of the reactants. But these guys are elements in their standard states, so their delta G's naughts of formation are equal to 0. So 0 plus 0, we don't really need to worry about this whole extra bit. So our delta G naught here of this reaction is just equal to the delta G naught of formation of NH3 times 2 because of the 2 here. That makes sense? At the end of the day, we can calculate value. All right, we look at those. Oh, look, this is 0 though, and this is 0. So we get the one we were given, multiply it by 2 because there was a 2 in the equation, and minus 0 from it. Hey, there we go. We got our delta G naught of the reaction. Now we were also told that the pressure of hydrogen was 0.75 atm, and the pressure of nitrogen was 0.5 atm, and the pressure of NH3 was 2 atm. Now all of these we can use to get Q. So we know Q is always equal to the products over the reactants. And in this reaction, we have NH3 over N2 times H2. But we have stoichiometric coefficients here we need to worry about. There's a square there, and there's a cubed here. And then we just got to take these other values that we were given, this one, and this one, and plug them all in. All right, so, and if we do that, we get an equation like this. All right, so we have our delta G naught of the reaction. This guy's this. We have our R value. That's that. We have the 298 we were given. That's our T value. And notice here, I'm making sure my units hold joules to kilojoules. That's like the biggest mistake in any problem here. R is usually given in joules, but this guy we calculated in kilojoules, so I'm converting joules to kilojoules here with this 1 over 1,000. My natural log I'm taking of Q, right? And Q is NH3's pressure squared because of the 2 in front of NH3 in the reaction times N2's pressure times 0.75, again cubed because of the 3 in front of H2 in the equation. And that gets me my delta G if we just kind of plug all that in and hit solve on our calculator. And you get this as our value, which tells me this reaction. Okay, so why are non-standard conditions worthwhile? Well, there are two reasons. The first one, we're generally not under standard conditions when we're working in the lab room. Our pressure is generally not exactly 1 atmosphere, and even when it is, that's usually the pressure of the air, the total pressure, not the pressure of each individual gas in our room. And generally the temperature is not exactly 25 degrees Celsius in the lab. So knowing how to calculate stuff under non-standard conditions is very valuable because generally you're not going to be under standard conditions when you're doing your experiments. The second thing is that reactions under standard conditions that are non-spontaneous can still happen under non-standard conditions. I can make a reaction that is normally not spontaneous under standard conditions be spontaneous under non-standard conditions. For instance, take water. When we think about water turning into a gas, right, going from the liquid state here to the gaseous state, we know this is a non-spontaneous process at 298 Kelvin, or in other words, 25 degrees Celsius. And hopefully that makes some sense. We're like, oh yeah, water in my water bottle in this room right now is not boiling spontaneously by itself. You know, that hopefully is pretty obvious. But if we think back and apply this knowledge a little bit, it starts to sound kind of funky, because if you've ever spilled water on a table and then like maybe you wiped up a little bit, but there were still water droplets on the table, and then you walked away, 20 minutes later you come back, those water droplets generally probably won't be there anymore. Well, what happened to them? They didn't just vanish into another universe. They evaporated. But if it's a non-spontaneous process at 25 degrees Celsius, how did they evaporate? I'm assuming that your house or wherever you spilled this water is not at 100 degrees Celsius, because you would be very badly burned and you should get out of there immediately. But so why did it evaporate? It didn't disappear, it evaporated. So why? Well, the key thing here is that your room or your house or wherever you spilled this water was not under standard conditions. And while under standard conditions, water does not evaporate at 25 degrees Celsius, under non-standard conditions, it very well might. For instance, we live in California, or this class is offered in California generally, and it's a desert, which means our humidity is very low. In other words, the amount of water in the air that we're breathing or in our atmosphere is low. Now, in order for us to be under standard conditions, the pressure of water, gaseous water in the air would have to be 1 atm. And while the total pressure in our atmosphere, as long as we're near sea level, is close to 1 atmosphere of pressure, the partial pressure of the water in our air is definitely not 1 atm. It's generally much lower than that, right? Generally, our pressure of water in at least Southern California in the air is around 0.03 atmospheres, so well below standard conditions. And it's for this reason that even though standard conditions, water is non-spontaneous and turning into a gas at room temperature, in the real world, where we're under non-standard conditions, water will definitely evaporate at 25 degrees Celsius, at least in California, where our pressure is not 1 atm of pressure for water in the air. So if you have any questions, as always, please email me or come to the discussion sessions.